So, in the previous lecture we have discussed about the approximate methods of modal analysis. One class of methods which is based on the energy, the kinetic potential energy, the Lagrangian, etc. So, which are broadly classified as energy based methods for modal analysis. Now, in today's lecture we are going to look at yet another class of methods which are known as projection methods. So, our motivation for studying approximate methods, we have already discussed that analytical methods, though they are more preferable, but are quite cumbersome, and we can have approximate methods which can give quick and sufficiently accurate results. So, in today's lecture we are going to look at these projection methods which work directly with the governing differential equation of the system. So, these since these methods work with the differential equations directly, they can be used very easily for dealing with non-conservative forces, non-potential forces, etc. So, since these terms they can be directly written in the equation of motion and they are little tricky to introduce in the Lagrangian as such, though they can be done in that way. But if a method works directly with the equation of motion, then these non-conservative terms and non-potential forces, they can be handled quite effectively. So, what do we do in these projection methods? So, let us discuss this in the context of this equation of motion. So, let us consider a differential equation which has a structure like this. So, mu x represents the inertia operator, let us say, and k is another linear differential operator. So, essentially what we are going to do is discretize. So, this is a continuous system, this is described by this partial differential equation. So, what we aim to do is to discretize this equation of motion. So, we use the idea of expansion of the field variable in this form. One thing that may be mentioned here, that even though this looks like a separable solution, but actually it is not, because this is an expansion. Had it been only one term, then it is a solution that is separated in space and time. But once you take this expansion, it is no longer a separable solution. Now, this may be written in terms of vector multiplication like this. Now, here in these projection methods, there is a restriction on the kinds of function in which using which we do this expansion. These functions are known as comparison functions. Now, what are comparison functions? These are functions that satisfy two important properties. They must be differentiable at least up to the highest order of space derivative in the equation of motion. The second important property that they should satisfy is that they satisfy all the boundary conditions of the problem. Now, this is very important to note that these functions must satisfy all the boundary conditions of the problem, and this actually makes this method a little more difficult to apply compared to the energy based techniques where we were using admissible functions. So, we expand our field variable in terms of these comparison functions and unknown coordinates of time. So, if I substitute this expansion in the equation of motion, then of course, I do not expect that this solution will satisfy this equation of motion, because in any case this is an approximate solution. So, what we generate is known as residue. This is known as the residue. So, this we do not expect that this will be 0 throughout the domain. So, this function is known as the residue. Now, we project this residue in a certain space. So, we are looking, I mean this can be thought of as expanding the solution as a linear combination of certain functions, as we had discussed previously as well. And so on. So, this point represents the configuration of the system, and as these temporal functions they change, this point moves in this space. Now, we have generated this residue because this solution is approximate. So, what we can do is we can try to make this residue 0 at certain points. Now, there are various ways of doing it. So, here we first introduce the idea of projection. So, we have a suitably defined inner product of two functions. So, one is the residue that we have generated and another function h of x, which we can simply define in this case and say that this projection is 0. Rather than the residue vanishing identically, we say that the projection of this residue on certain functions that we will qualify shortly. So, this projection is 0. Since we are searching for approximate solutions, so we this solution structure that we have considered, that is approximate, since it is finite expansion. Once we substitute that in the equation of motion, we generate this residue, since this will not be identically 0. So, what we say is, instead of having this identically 0, we have a weaker condition which says that the projection of this residue along certain function directions, this is 0. So, that is, so we can take n such functions suitably chosen to generate n equations, and thereby we can attempt to solve for this n unknowns p k that we have in the expansion, the temporal functions. Now, this choice of these functions h, that decides the method. So, what are the different ways of choosing these functions on which we project? The simplest choice is this Dirac delta function. Once we choose these functions as these Dirac delta functions, this method is known as the collocation method. Now, what does it mean to choose h j as Dirac delta functions. So, if you substitute these functions here, then what you will obtain is what this means is that this residue is 0 at certain points, not at all points, but at certain points over the domain. Say for example, for the bar, if I choose these x j these points, something like this. So, at these points the residue must vanish. So, now there can be various ways of choosing. So, these points are known as the precision points. Or also sometimes known as accuracy points. Now, there can be various ways of choosing these precision points or accuracy points. They can be uniformly distributed, or there can be other methods of choosing precision points. A good way of choosing precision points is given by Chebyshev method. And they are known as Chebyshev accuracy points. Now, let us first look at what happens when we substitute this residue in the projection equation. So, I rewrite the residue, and if I consider the projection the functions like in this form using Dirac delta functions, then we arrive at this equation of motion. This is the discretized equation of motion, where this matrix elements are obtained like this. So, when we use collocation method, we obtain this discretized system where the matrix elements are given like this. So, let us once again look at the example of the tapered bar. So, here we have the fixed free bar once again, and we have the geometric boundary condition at the left end and the natural or dynamic boundary condition at the right end. Now, we have to choose functions which we have to choose the comparison functions which satisfy. So, comparison functions will must satisfy the boundary conditions, all the boundary conditions of the problem, which means they must satisfy the geometric as well as the natural boundary conditions. So, let us look at particular choice as shown here. So, we have these functions p j. You can check very easily that so p j of x so you can check so they satisfy so these functions satisfy the geometric boundary condition as well as the natural boundary condition at the right end. Now, we can choose these accuracy points as we have discussed. We can choose them as uniformly distributed, so if you divide the domain of the bar in n parts, then you can take these uniformly distributed, or you can also have the Chebyshev accuracy points, which are determined by this expression. Now, this has a nice geometric visualization. So, this is the domain of the bar. So, if you draw a semicircle with this domain as the diameter, and you put in a regular polygon. For example, if you want to take 3 accuracy points, you have to inscribe half a hexagon, and the projection of these corner points on the domain will give you the accuracy points. So, this is the Chebyshev, these are the Chebyshev accuracy points. So, as you can see, these Chebyshev accuracy points will never fall on the ends of the bar. So, once you use either this uniform spacing or the Chebyshev spacing and calculate the eigen frequencies. So, for uniform spacing, what you obtain So, these are the first two circular natural frequencies. When you consider uniform spacing, when we consider Chebyshev spacing, then the first two natural frequencies are obtained like this. However, if you look at the exact circular natural frequencies, they are obtained like this. So, here what we find is the fundamental circular natural frequency is in some error from the exact circular natural frequency, while the second one is more close. Now, this collocation method has this disadvantage that this does not have that upper bound property as we saw in the energy based methods. So, this approaches the exact natural frequency from below, but I mean it can also, for example, if you see this comparison, this is approaching it from above. So, this is a disadvantage of the collocation method. Now, if you calculate the eigen functions corresponding to these eigen circular natural frequencies, then what we obtain is shown in the screen. So, if you look at the fundamental eigenfunction, the eigenfunction corresponding to the fundamental mode, then within the accuracy of this plot you see you cannot distinguish the exact method with the collocation method, though the natural frequency is in some error, but this can of course be rectified by considering more and more terms in the expansion and making it more accurate. On the other hand, if you look at the eigenfunction of the second mode, you see with the Chebyshev spacing it appears to be more accurate, because the location of the node matches quite well with that obtained from the exact solution, while that of the uniform spacing is in some error. So, we have looked at, so this choice of, we have looked at one choice of the projection functions h of x. Now, we will look at another choice which gives us what is known as the Galerkin method, which is another powerful method which uses the projection technique. Now, in the Galerkin method, so remember that we have expanded where these these are comparison functions. Now, then we generated the residue and we projected the residue on certain functions and put them to 0. Now, in the Galerkin method, we take these projection functions same as the comparison functions we used for this expansion of the field variable. So, this so this projection gives us these n equations from which we are going to solve for these n temporal functions p of t. Now, this so when we choose this projection functions as same as the comparison functions in the expansion, then we have the Galerkin method, and when we do this projection, we obtain this discretized equation of motion, where these matrices M and K are obtained in this form. So, this structure, so this is again so we obtain the discretized equation of motion of the system. Now, let us look at this example once again. So, these are the boundary conditions at the fixed and the free ends. So, once again we choose the comparison functions we will take two comparison functions and discretize the equation of motion. So, if you do that, you will obtain the discretized equation in this form. Then, as usual, we do the modal analysis assuming this structure of solution, and we obtain the eigenvalue problem, discretized eigenvalue problem, and from where we obtain the first two circular natural frequencies. Now, this superscript g indicates obtained from Galerkin. Now, if you compare so, as you can see that the fundamental frequency compares very well with the exact, while the second modal frequency is in some error. Now, here again, if you want to have accurate modal solutions for the first n modes, you use an expansion with 2n terms. So, here we can see that the error in the fundamental frequency is very small as compared to the second frequency. Now, when you solve this eigenvalue problem, you also obtain the eigen vectors k. Now, these are obtained So, one can easily determine these eigenvectors corresponding to the two eigenfrequencies and the corresponding eigenfunctions. So, the eigen functions are these eigenfunctions are obtained as using these eigenvectors So, for the first eigenvector for the first eigenfunction you use the first eigenvector in this vector product. Similarly, for the second eigenfunction use the second eigenvector in this vector product. So, these are the two eigenfunctions that are obtained from the Galerkin method. Now, here we can see a comparison of these eigen functions with the exact solution that we had obtained previously. So, as you can see within the accuracy of the plot the fundamental eigen function is indistinguishable from the exact. Fundamental eigen function solved from the Galerkin method is indistinguishable from the exact solution. For the eigen function of the second mode, this is fairly close, and you can see now that the boundary condition at the right end, the free end, is also matching, though the location of the node is in slight error. So, in these plots we have compared these two eigen functions obtained from the Galerkin method with the exact solution. Now, this Galerkin method, since as we discussed that this is a method for discretizing the equation of motion of a continuous system. So, we can use this also when we have external forcing, and which we will discuss later on in this course. So, to summarize, we have studied in this lecture projection based proximate methods, which in which the field variable is expanded in terms of comparison functions and substituted in the partial differential equation of motion of the system. Then what we generate is the residue, and this residue will not be 0 uniformly over the domain. So, we use a weaker condition, we project this residue onto certain functions, and the choice of these functions decide the method. So, when we use the Dirac delta function, we have the collocation method, while if you choose the comparison function used in the expansion of the field variable themselves as the projection functions, then you have the Galerkin method, and these methods or the projection methods, they can handle non-conservative and non-potential forces. So, with this we conclude this lecture.